Hey guys, I wanted to continue our lesson on light and start talking about reflection, which is a major focus of the chapter. I decided I want to do one lesson on reflection, and then we're going to have another lesson at the end of the week on refraction of light, which is really important for the application of things like lenses. Um, so the big thing about reflection we think of mirrors right away with reflection, but there's actually a lot of different ways that we can consider reflection. So we talked about in our previous lessons about the speed of light and the wavelength of light, and how light exists as a wave. But for this, we're really going to consider that light is moving in a straight line, like a particle almost. So this is kind of another major aspect of light. So light, like all waves, can reflect off of things, and it mostly just depends on the geometry or the nature of the surface. We think of light coming off of something that kind of you're getting the intensity of the light, but not necessarily an image of what you're seeing. And that's called diffuse reflection. That would be like off of maybe a white piece of paper reflects a lot of light, but you can't necessarily see an image because it's not polished. On a molecular level, there's actually lots of little hills and valleys. Something like a mirror or the surface of a lake or metal or something like that is more of a straight reflection. The image can form here because all the light is sort of entering parallel and exiting parallel. So even though that changes directions overall, it's all changing direction the same amount, not like diffuse reflection. So there's a huge branch of physics that deals with geometry of mirrors. I actually took a whole course in college called it was called optics, and we did a lot with lenses and mirrors, which is kind of an interesting class. So we, for something like a mirror, something that's reflective, we assume that basically all the light is kind of reflecting off, and we're not diminishing our the intensity of light or anything like that. We know in reality, you can see from this golf ball image that light actually does decrease in intensity because not 100% of it is being reflected. A small amount of it's being absorbed or reflected diffusely or something like that. But we make these assumptions about how light basically is just continuing forever in whatever direction it's reflected. And this is something that you probably already knew to be true, but maybe hadn't considered it. That the incident, the angle of incidence, as we call it, however far the angle is from being straight on or normal to the surface. Normal means perpendicular to a plane. The farther away that angle is, the farther away it's going to reflect. So if you shine it in real shallow, it's going to reflect real shallow. If you shine it normal or perpendicular, it's going to reflect perpendicular. So that would be a 0-degree angle if it was normal, or it'd be almost a 90-degree angle if you were kind of shining it along the surface. So for lenses and mirrors, we always measure from the perpendicular, or from the normal, as we call it. Okay, so the result here is that we can see an image in a mirror, right? Most of the time, we consider mirrors, the mirrors that we encounter on a daily basis, are flat mirrors. So flat mirrors, the object always appears the same distance as the image is from the mirror. So when you're looking at yourself in the mirror, if you're standing 2 feet from the mirror, your image will appear 2 feet behind the mirror. So the cat maybe just a few inches above the mirror, but the image of the cat that it's seeing appears to be 2 inches behind the mirror. Now, for all lenses and mirrors and everything, we talk about the image as being in an actual position. We know that the cat isn't really behind the mirror, but we can work out the geometry to a real location there. Even if there's just a table or something underneath, we can work out location that way. People who manufacture telescopes and binoculars and things like that have to account for an actual location for an image, even if it's not physically coming from there. Okay, so for a flat mirror, it's always equal. The object and image are equal distance from the mirror. Okay, so why does this happen? Well, if you think about, remember that light, we see an image because of where the light is coming from. and your eye can't tell if it's reflected off of something or not. Okay, so you think about how your light is reflecting off the mirror. So a light ray coming from the top of your head hits the mirror and comes almost straight back to your eye. So it looks like it's coming from someplace way behind the mirror. Okay, again, your eye can't tell that it's bounced. It only just assumes that all light has traveled in a straight line. Okay, similarly, if a light from your foot bounces up and hits your eye, your brain is interpreting that as, oh, that came from way behind in a straight line from my foot across the way. And you work out some geometry and you realize that your mirror image and you have to be equal distance. Okay? And so you're never, in a mirror, you never appear to be shrunken or magnified in a flat mirror. But this is a little bit different when we're talking about curved mirrors. Okay, so I want to talk about curved mirrors as well. So this is another example of a flat mirror, but I wanted to show you kind of how this works. We usually use something that's simple to draw, like a candle or a pencil, to represent the object, which we use the letter P, and an image, which we represent Q, which is convenient because the mirror image of P is Q, right? So this is just sort of the same sort of thing. Another thing that we talk about is the height of the object and the height of the image. For a flat mirror, they have to be the same. But things get a little bit different when we start talking about curved mirrors. A little bit different, because if you put an object in front of a curved mirror, the light is going to not all reflect parallel in or out. Okay, so the most important one is what we call a concave mirror. And you probably have a concave mirror in your home as like a makeup mirror or a shaving mirror. Your face always seems to be sort of distorted in size depending on how close you hold the mirror to your face. Those mirrors are concave. You can remember caves. I always got concave and convex mixed up. Caves go in. So a concave mirror bends in, okay? And these can do two things to images depending on where you put it. So let me show you what the different parts of a concave mirror are. Okay, so a concave mirror can do two things. If you're standing very close to a concave mirror, we say inside the focal point, it appears to magnify your image, but keep it upright. Okay, so here's this little toy here where the penguin appears much larger in the mirror. The image is being magnified, and the same as this hand. The hand is inside the focal point, but it seems to be upright. But if you stand some distance away, outside the focal point, what ends up happening is the image gets flipped over. So you notice if you ever look at your image in a spoon, if you ever hold a spoon, such that you're facing the cupped part of it, your reflection is always going to be upside down. Okay, so out some distance away, it flips the image over. So this is a really good image here of this woman holding her hand in front of a concave mirror. Her hand looks much bigger because it's real close, but look far away. There's this bench that's upside down. So concave mirrors flip distant images, but magnify close images and keep them upright. Why does this happen? Okay, so if we think about a concave mirror as being a circle, what we can do is we can define a couple different parts. Okay, so if this was a circle, this would be the center, and the focal point is always half the distance to the mirror, so half of the radius. Okay, so not half the diameter, half the radius. Okay, and what happens is if we have an image, let me just insert one here real quick. Okay, and I'm just going to stand him some distance back from the mirror. So we'll say he's outside of the focal point. Okay, we'll think about how his light is going into the mirror and how it's coming out of the mirror. So I'm going to draw some arrows here. So if I have light coming from maybe his head, we'll say, going straight into the mirror parallel to the surface, what's going to happen with that light is it's going to bounce through the focal point. That's what the focus does. Okay? I'm going to make it real long here. Okay? And if he has light going in through the focal point, so maybe at some other angle, but I'm just going to happen to make it through the focus, it's always going to bounce out parallel. So the result is these two lines cross. I'm going to make this one a little bit shorter so it's more obvious. These two lines cross right here. So what he's going to see is an image of himself, but look, it's on the other side of where he's standing. So he'll appear to be upside down. So what's going to happen is he's going to see an image of himself that's a little bit shorter and upside down, okay, because it looks like it's bouncing from there, and it will appear kind of right, it will appear closer to him than it actually is. So this is sort of a weird effect. So if he's standing outside of the focal point, this is what happens. Okay. A bizarre thing happens when he gets real close. Okay. So how is this going to work? Well, we got to follow the same rules here. So light going, oh, I don't want black. Light going in parallel is going to reflect through the focal point. Okay. And light going in through the focal point will reflect parallel. But wait a second, that can't happen. How am I going to do another line going through the focal point? Well, what I'm going to do for that is a little bit different. I'm going to make it appear that it's coming from the focal point up this way, okay? And now it's got to bounce out parallel. And you say, well, these two lines, this one way out here and this one way out here, are going away from each other. They're not going to form an image there, okay? But remember, your eye can't tell where it's come from, okay? So really what's going to happen is it thinks that the image is coming from back here. I'll make that one dotted. So your eye thinks it's coming from back here, and also thinks that this one is coming from back here. Okay, so you're actually going to appear enlarged in the mirror in this case. So it's going to appear that you came from behind the mirror, so you're upright, but you're actually a little bit larger. This is why a makeup mirror actually enlarges you, but you have to make sure that you're holding it close to your face. Okay, I'll talk about convex mirrors in another video because YouTube's going to cut me off here.